Okay, picking up where we left off, we're going to use the limit rules to go through and prove a couple of results for polynomials and rational functions. Let's take a quick look at them before we get into this. Remember, limit of a sum is the sum of the limits. Limit of the difference is the difference of the limits. We can bring constants outside of limits. Limit of a quotient is the quotient of the limits, provided we don't have 0 as a limit in the denominator, and we had the power rule. The limit as x approaches c of f of x to the n is the limit as x approaches c of f of x, quantity, to the n power. So those rules are used in establishing the following. Theorem 2.2, we'll use this a fair amount, says limits of polynomials can be found by substitution. So if we have p of x equals a polynomial a sub n x to the n plus a sub n minus 1 x to the n minus 1 down to a multiple of x plus a constant term, then the limit as x approaches c of p of x is p of c. All you got to do to evaluate a limit for a polynomial, the claim is substitute in for x the value c. Should make sense when you think about x being close to c. We should get function values that are close to p of c. Nothing goes wrong in terms of substituting in. I ain't saying you evaluate limits by substitution. Made a big deal out of the fact that it doesn't matter what happens at c in general. Sometimes there's useful information at what happens at x equals c, but it depends on the function. For polynomials, you can evaluate limits by substituting in. For polynomials, actually in Theorem 2.3, so here we're getting some basic facts down about limits. It says limits of rational functions can be found by substitution if the limit of the denominator is not 0. So big if, of course, you can't divide by 0. In other words, if we have a rational function, rational functions are of the form p of x over q of x. Rational functions are ratios, and that's why the rational starts with the first few letters ratio. It's a ratio of polynomials. And if we have a limit as x approaches c of the ratio p of x to q of x, where p and q are polynomials, and the denominator q is non-zero at x equals c, then we can evaluate that limit by taking a limit of the quotients, which we just saw. We can evaluate by plugging in the values c because p and q are polynomials by the previous result. Provided you don't get 0 in the denominator. Okay, so the subtleties are piling up. I didn't say you can evaluate limits by substitution. We said in polynomials, you can evaluate limits by substitution. And in rational functions where division by 0 isn't an issue, you can evaluate limits by substitution. And that's it. So substitution works for these two special kinds of functions. Let's go through proofs of both of those and then a couple of examples. Okay, for polynomials, we'll use the limit rules as promised. A limit as x approaches c of p of x. Okay, so limit as x approaches c of this. This was the definition of p of x as given in the statement. And look at this, you got a limit of a sum of a bunch of things. Well, the sum rule tells you we can write the limit of that sum as a sum of a bunch of limits. Again, not distribution, it's the sum rule for limits. Theorem 2.1, part 1. Okay, let's see at each of these. We've got these constant multiples. The coefficients, the a sub n minus 1, a sub 1. We could bring those out front using the constant multiple rule. So bring the scalars out front. That leaves you with a limit as x approaches c of x to the n. A similar limit, x to the n minus 1, a similar limit of x. Okay. Hey, here we've got a function raised to a power, simply x raised to a power in each of these. The power rule dealt with that. Okay, copying what we had from the previous slide, for these lengthy computations. The power rule says, hey, you want to take a limit as x approaches c of x to the n? We can treat that as a limit as x approaches c of x to the n. So there's how the powers rule is used throughout for each of those powers of x. And we don't know a whole lot about limits rigorously just yet, but we did make an observation that the limit as x approaches c of x is simply c. The identity function, we dealt with that one, see note 2.2.a, and we observed that the limit of a constant function is that constant. So that note justifies replacing x with c in each of these parenthetic things and saying the limit of a constant is that constant, dropping the limit and replacing it with an a sub 0. And if I clean it up just a little bit, get rid of the parentheses, that's exactly the polynomial evaluated at c. So limits are easy to evaluate for polynomials. Yeah, nothing can go wrong with a polynomial. Your limitations at this stage are you can't take square roots of negatives because I won't let you, and you can't divide by 0 because nobody can. Well, in a polynomial, there is no square roots and there's no division related to the variable. So there's no problems with those things going wrong in a sense. Let's look at Theorem 2.3, similar type result, except this time deals with the rational function p of x divided by q of x. Divided by, I'd worry about division by 0. And the real punchline in this one is, if nothing goes wrong, you can evaluate a limit by substitution in a rational function. And the only thing that could go wrong in a rational function is division by 0. And if that does go wrong, you can't use this. Okay, proof of this one actually is super quick because we know how polynomials behave. All right, we know for polynomial p of x, the limit as x approaches c of p of x equals p of c. You can evaluate that limit by substitution for that polynomial p, because that's what the previous result showed. You can evaluate that limit as x approaches c of q of x, because q of x is a polynomial, by substitution, same reason. Also, we know that q of c is not 0. The limit of that denominator is not 0. That was part of the necessary hypotheses. So the quotient rule says the limit of a quotient is a quotient of the limits. If you don't get 0 in the denominator, we don't get 0 in the denominator. We get q of c in the denominator, and that's not 0. So the previous result combined with the quotient rule tells you evaluation of limits of rational functions, piece of cake. If you don't get 0 in the denominator, you can do these by substitution. What if you do get 0 in the denominator? Well, then you can't do them by substitution, but you might still be able to evaluate the limit. The limit might still exist, not because you can divide by 0, but because of some other things previously discussed and discussed in the future. I could maybe do some modification of the function. I could take a function that yields division by 0, introduce a different function that doesn't involve division by 0, but that different function is the same as a given function, maybe except at point C. And we've already done a couple of these. So beware what this says. It says, if you don't get division by 0 in a rational function, you can evaluate limits by substitution. It doesn't say anything about what happens if the denominator has a limit of 0. The limit may not exist. The limit may exist. The function certainly doesn't exist, and you can't substitute if you do get division by 0. So be careful with what it says. Let's illustrate both of those. Okay, piece of cake here. Evaluate the limit as x approaches -2 of this thing here. This thing here is a polynomial function. So to evaluate the limit, all you got to do is plug in the -2. Plug in the -2, do the arithmetic. Apparently you get -16. Does that tell you anything about this function? I guess it tells us it tries to pass through the point -2, -16. Does it succeed? Not relevant to a limit question, but does it succeed? Sure, it's a polynomial function. It's defined at -2, and that is the value of it. It tries to pass through the point -2, -16. By the way, it succeeds. How about this rational function? Evaluate the limit as y approaches 2, y plus 2 over y squared plus 5y plus 6. Well, the second theorem, theorem 2.3, second theorem that we dealt with, told us we can do this by substitution if we don't get division by 0. So let's go through it one piece at a time. Let's call it r of y for rational function. R of y equals p of y over q of y. They've chosen y as the variable instead of x, but whatever. Treat this as the rational function. Then let's concentrate on the numerator and the denominator. Numerator is the polynomial function y plus 2. Denominator is the polynomial function y squared plus 5y plus 6. We know by theorem 2.2 that dealt with polynomials, the limit as y approaches 2 of p of y, that is, the function y plus 2, can be evaluated by substituting the 2 in, that is 2 plus 2 equals 4. The limit of q of y, since it's a polynomial, can be evaluated by substitution. Do the arithmetic, and I guess we get 20. And the important thing about 20 is, in this setting, it ain't 0. Okay, so we won't get 0 in the limit in the denominator. We'll get 20. So that's why that's pointed out. So we can use theorem 2.3 that says, hey, limit of the quotient of the limits, as long as you don't get 0 in the denominator, you don't get 0 in the denominator. We just saw that you get 20 in the denominator. And we had 4 in the numerator, so we get 4 divided by 20, which simplifies to 1/5. So piece of cake to evaluate limits for polynomials and rational functions when the rational functions don't involve division by 0. The real punchline then is, well, these ain't very interesting functions for limit stuff then. All you do is substitute numbers in for polynomials and rational functions that don't involve division by 0. So we want to look at more interesting functions that are more complicated when evaluating limits than simply substituting in. But it gives us a foundation to deal with other things. Back to the notes. Okay, we did those 2 examples. All right, we're going to do something I call factor cancel substitute. We now state a result that allows us to evaluate most of the limits that we'll encounter in the first part of Calculus 1. Not all, even here though. It'll allow us to apply the technique of factoring, canceling, and substituting, FCS. All right, and this is justified really by some of the more rigorous stuff, some of the things we'll see in section 2.3, the next section. But here's my statement. Dr. Bob's limit theorem, theorem 2.2.a, says if functions f and g satisfy the fact that f of x equals g of x for all x in an open interval containing c, except possibly at c itself, then the limits are the same. So this is a slightly more formal way of some things we observed before. The functions are maybe different, but the limits are the same. Where are these functions different? Well, they might be different at C, and they might be different far from C. But close to C, except for C itself, those 2 functions are equal. That's what this stuff about the open interval means. Hey, open interval containing C contains points close to C and a little bit less than C, and contains points close to C and a little bit bigger than C. And that's the values of X you consider, except possibly C itself, when you consider limits. So the formal definition of limit will make this, will justify this claim. Okay, so what we're going to do then is find functions that are equal in this setting and take the limit of a function that's not very cooperative and turn it into a nice cooperative function. A function I can evaluate the limit of by substituting, which is polynomials and rational functions that don't have denominators of 0. It'll justify the cancellation stuff. And we started this conversation with a very conservative approach about canceling factors, because we can justify the cancellation in limits. We can't justify just outright cancellation all the time and say we've got the same functions as observed earlier. Okay, the book describes this slightly differently. Dr. Bob's limit theorem is a summary of what the book calls eliminating zero denominators algebraically. It's the cancellation stuff that I'm justifying. They're calling it this thing about eliminating zero denominators. You better not have zero denominators. So I object a little bit to that verbiage, actually. And they call these things simpler fractions. Yeah, they've factored and they've canceled, and they're looking for a justification. As it is, Dr. Bob's limit theorem will act as our justification. Something else in the book that we're just not going to do. The text talks about using calculators and computers to estimate limits. What they do is they plug in x values closer and closer to c, and then they guess what the limit is of the outputs. That can be horribly misleading. Now, I got to go to some exotic links, but I'll do it to come up with a function that can mislead you. And we'll see an example of one in the next section or two. We'll just skip these exercises about make a table. I mean, it's just playing with a calculator and looking for a trend in the numbers. Yeah, if there's a trend there, you'll probably see it. If there ain't a trend there, you might still see a trend there is the problem with this stuff. We're going to do this cleanly and rigorously. And it'll become pretty routine here. Once we get a technique to go through and deal with this, the algebraic manipulations are not complicated. The ideas are way deep. That's why we're spending all this time going through this motivational stuff and this wink, wink, informal stuff. Let's look at a couple more examples and see what's up with this. Okay, evaluate that limit as x approaches to, as v approaches to. Limit as v approaches to, v cubed minus 8 over v to the fourth minus 16. Well, that's a rational function. We can just plug in v equals 2 unless we get 0 in the denominator. And if we can just plug in v equals 2, this ain't a very interesting limit. Oh, look at that. You can't plug in v equals 2. You plug in v equals 2, 2 to the fourth power, that's 16. Yeah, you get division by 0 when you plug in v equals 2. So you can't plug in v equals 2 because you can't divide by 0. We've been through this. So it's not as simple as just substituting, even though we have a rational function. It's not a rational function to which theorem 2.3 applies because you get 0 in the denominator. So of course you can't just substitute it in. This one's more interesting. All right, let's apply Dr. Bob's limit theorem. And we're going to factor, cancel, substitute, justifying each of those manipulations. The factoring, you know from your background, the canceling will justify with Dr. Bob's limit theorem, and the substitution will justify with one of those two theorems we just saw. Recall, quote unquote, recall, you've seen this in the past, but if you have the difference of two perfect cubes, you can factor as a minus b times a squared plus ab plus b squared. The difference of cubes identity, I looked in the book and I couldn't find it mentioned anywhere explicitly. Previous editions had it written out explicitly, but anyhow, an identity from your background that tells you how to deal with a difference of two perfect cubes. So we can factor v cubed minus 8, that is v cubed minus 2 cubed. We can factor as v minus 2 times v squared plus 2v plus 2 squared. So we're taking a equal to v and b equal to 2. If I want to compare like that, and that's where we get the factoring. Let's take that 2 squared and go ahead and write it as a 4. Then that's the factoring as related to the numerator. So we can take the limit as x approaches 2 of the given function, take the v cubed minus 8, and replace it with this. So there's the factoring of the numerator. Hey, the denominator is a difference of two perfect squares. This you remember, I hope. And that we can write as the first minus the second times the first plus the second, taking square roots of both of these. So we'll deal with a v squared and a 4. So we get v squared minus 4, v squared plus 4. Foil it out, and indeed you'll get v squared squared, v to the fourth, minus 4 squared minus the 16. So difference of two perfect squares. Actually, here's another difference of two perfect squares, and that v squared minus 4. Okay, well then let's take the v squared minus 4. Let's factor that as well as a difference of two perfect squares, v squared and 2 squared, and write it as v minus 2 times v plus 2. So I just listed it as two separate steps. I think it's easier to follow. So we got it factored. Let me put a little asterisk by that. We had a threefold strategy of factor, cancel, substitute. The factoring's done. All right, so copying what we had from the bottom of that previous slide. Now what? Can you plug in v equals 2, by the way? It's still a rational function. No. Actually, I see why I can't plug in 2 very explicitly. It's this thing right here. It's that v minus 2 that's causing the problems. So that's why you can't plug in v equals 2. Hey, but there's a v minus 2 in the numerator as well. Can you cancel those, creating a different function? Where will the function be different? Function will be different only at 2. If I cancel these, change this function into this function by canceling the v minus 2 factors, those are different functions. How so? Well, this one's not defined at 2, and this one is. I plug 2 into this. Well, I can't plug 2 into this because I get 0 in the denominator. I plug 2 into this, and I don't know what I get. I don't get 0 in the denominator, so I'm good to go. There's some other places these two functions aren't defined, but that's where they're different. The only place there's different is at 2. And we're taking a limit as v approaches 2. So I don't really care what happens at v equals 2. Different functions, same limit. Dr. Bob's limit theorem says these functions are the same on an open interval containing 2, except at 2. They're not the same at 2. Forget the possibly not the same. They're not the same at 2 because that one's not even defined and this one is. That justifies canceling. This offer only valid in limits. Dr. Bob's limit theorem says the limits are the same even though the functions are different. It's how they're different, not much. Let's give that one a couple of asterisks. Here's where we've done the cancellation. Okay, now we've got a limit of a polynomial divided by another polynomial. We can evaluate those kinds of limits by substitution. It's a rational function, provided we don't get 0 in the denominator. And we don't get 0 in the denominator. The v minus 2 was causing the problems with zeros in the denominator. It's gone. We canceled it. So we can substitute because we have a rational function that doesn't produce 0 in the denominator. So let's give that one a little 3 asterisks. Substitute in, do the arithmetic, simplify a little, and I guess we get 3/8. So we factored, we canceled, and we substituted. And that's a common way to evaluate limits here in the beginning. Put a little box to indicate I'm done with a problem, but let me reiterate. Here's the 3 steps. Here's where we had factored. Here's where we had canceled. And here's where we had substituted. The factoring, you know how to factor stuff. The cancellation, Dr. Bob's limit theorem allows you to justify the cancellation. Substitution, somebody's got to allow you to do the substitution. For now, we can justify the substitution provided we have a polynomial or a rational function that doesn't give 0 in the denominator. So it should be straightforward in terms of factoring. I mean, factoring can be tricky, but you'll be given textbook examples, quite literally. Factoring can be tricky, but it's just algebra. The cancellation we can justify. The substitution, actually it's a substitution that might be tricky to justify. Here, rational function, good to go. You have to be careful when substituting to avoid division by 0. Square roots of negatives, you know, are going to be a problem. Logarithms of 0, logarithms of negatives are going to be a problem. Or other forbidden mathematical maneuvers. Tangent of pi halves isn't defined, for example. Maybe the sine inverse of 3 isn't defined. I mean, other things can go wrong. Right now, your concerns are division by 0. We might run across some square roots, and square roots and negatives might be an issue before long. But for now, it's mostly division by 0 that we're interested in. So you got to have a reason to justify the substitution. Right now, our only reasons are because we have a polynomial or because we have a rational function that doesn't give division by 0. Okay, is it time to do another example? Yeah, let's go ahead and do that next example as well. All right. Limit as x approaches -1 of this thing here. Yeah, well, there's a square root. Can you plug in -1? No, you'd get division by 0. Also, no, that's not a rational function. All right, so gee, the square root messes some things up. But we had a root rule as well. So maybe we'll go back and look at that at some point. All right. This one requires a trick, and that's the reason I wanted to include this one in the examples. Turns out we can factor, cancel, substitute on this one as well. But you got to be clever about it, and you first got to multiply by what's commonly called a conjugate, conjugate of the numerator. You've maybe done this kind of thing before when rationalizing denominators. Here we're doing something to the numerator. So you would believe the following computation. Unmotivated, I grant you, but you'd believe I could take the limit and multiply by this parenthetic expression. Let's take square root of x squared plus 8 plus 3. Sorry, let's take the square root of x squared plus 8 plus 3. Divided by itself. I mean, after all, that's just 1. Whatever x is, that's just 1. Notice there's no square root of negative concerns here. X squared is positive, and then you add 8 to it. So we don't have issues over square roots of negatives anywhere in any of this, in fact. So I multiplied by 1. You can't argue with the validity of that. You can argue with the motivation of it. Well, here's the motivation. Okay, so what's going to happen is going to do the FOIL deal. We've got a thing 1 minus thing 2 times thing 1 plus thing 2. You know, there's cancellation, FOIL it, you get the first, the last, the outer and the inner cancel out because of the locations of the positives and negative signs, the -3 and the +3. So multiply out, you'll get the first squared minus the second squared. The center terms are gone. Gee, the denominators become a little more unwieldy. But hey, look what happens in the numerator. That square root thing got squared. That just yields the x squared plus 8 part. So the numerator got better. The denominator got worse. Was it really worth it? X squared plus 8 minus 9. To the arithmetic, that becomes x squared minus 1. There's a difference of two perfect squares. Get used to it. These things commonly arise, these difference of two perfect squares. We can factor that as x plus 1 times x minus 1. Denominators remaining messy. Ooh, there's the factoring part. So why did we multiply by this? Because it allowed us to factor in hindsight. Can you plug in x equals -1 now? Well, first off, it ain't a rational function, so no. Secondly, well, you get division by 0. It's that x plus 1 that's causing the division by 0. The same x plus 1 we started with. Oh, but wait a second, there's an x plus 1 in the numerator as well. Can you cancel those? Sure, by Dr. Bob's limit theorem. I can cancel the x plus 1s. And that kind of fixes things. The division by 0 stuff, we just got rid of it. You're welcome, Dr. Bob's limit theorem. So do the canceling. So there's the factoring, there's the canceling. Can you substitute in? Well, I can substitute in if we have polynomials or rational functions. This ain't a polynomial nor a rational function. The square root stuff tells you it's not a rational function. But we got a root rule. So to deal with this, first, let's take the limit of this quotient and write it as a quotient of limits. The quotient rule says we can do that. Okay. What's up with the substitution thing? Are you good at substituting in? Apparently, but I can justify that with the root rule. So we're looking at the function x squared plus 8 square root of plus 3. So let's concentrate on the x squared plus 8 square root of stuff. Okay, let's run back and look at the root rule. The root rule states in the notes, back upstream some. Remember, I had stated things a little bit differently than the book did on this root rule deal. Says the limit as x approaches c of, say, the square root of f of x equals the square root of the limit. If, when n is even, which it is when it's 2, when we're talking square roots, we also require that f of x be greater than or equal to 0 on some open interval containing c except possibly c itself. All right, so that thing we're taking the square root of, x squared plus 8 is what it was. We need to make sure that's greater than or equal to 0, close to whatever the c value was. Back to the proof. We're taking a limit as x approaches -1. Here's the x squared plus 8 part. Is that non-negative when x is close to -1? Yeah, it's non-negative all the time, in fact. So we can evaluate the limit of the square root by taking the square root of the limits. Square root of the limit. The x squared plus 8, that's a polynomial function. Its limit can be evaluated by substitution. Substitute the -1 in, justified by the fact numerator's a polynomial, denominator's a square root of a polynomial. It's a sum as well. So I could use a sum rule and a piece of this with a +3 stuff. But you can substitute in. There's your justification as to why. More complicated this time. This is usually the complicated part in terms of justification. And simplifying, I guess we get -1/3. But notice within the square root, we get -1 squared plus 8. That's the square root of 9, which is 3 plus 3 is where the 6 comes from. We don't get square roots and negatives. We get the square root of 9. So no problem with square roots and negatives. We got the square root of 0, might get a little bothered, because if we're getting square roots of 0 and the x's are moving around, we might be having square root of negative problems. But there ain't no negatives close to 9. So taking a square root of 9 in a limit setting, no problem. More on square roots of 0 later on. I didn't say you can't take the square root of 0. I said I'm getting worried when you have a limit involving the square root of 0 because close to 0 are negatives. But there are no negatives close to 9. So we're good. And here's the justification as to why. Back to the notes. Okay. All right. So we're going to shift gears a little bit and look at a different property of limits. I'm going to make a statement that can be justified in the next section. There's a proof of it in the appendix, I think. The next result lets us calculate the limit of a certain function that's sandwiched between two other functions, where we know the limit of the two functions related to the original one in a certain way. This we'll use for now probably mostly with trig functions. Okay, here's the statement, and picture worth 1,000 words. This picture's worth all these words. So think geometrically, and you're good on the sandwich theorem. Sandwich theorem says, let g of x be less than or equal to f of x be less than or equal to h of x. You know this part's coming. For all x in some open interval containing c except possibly c itself, because that's how these limit things are always worded. What's this mean, this inequality? It means close to c, except possibly at c itself. Down here in the picture, we got the g of x function on the bottom, the f of x function in the middle, and the h of x function on the top. Lesser, greater, sandwiched between the two. So we got the g function below, the h function above, and the f function, the one we're interested in, sandwiched between those two. Suppose also that, so additional hypotheses, the limit as x approaches c of g of x equals the limit as x approaches c of h of x equals L. What's that mean? Means the g of x function tries to pass through the point c comma L. C comma L, the g of x function tries to pass through that point. Limit as x approaches c of h of x equals L. Means the h function also tries to pass through that point. What's the conclusion? Well, it's the obvious thing, given the picture. The limit as x approaches c of f of x equals L is the conclusion. Well, yeah, h of x, think of it, h of x comes down here and tries to pass through that point. G of x comes up and tries to pass through that point, reading left to right or right to left, whatever. And f is sandwiched between the two, so it's going to be forced to try to pass through that point as well. So think of it in terms of limits, meaning the graph tries to pass through a point. Dr. Bob's anthropomorphic definition of limit, and you're good to go on a conceptual understanding of this. Yeah, well, we'll do our best to give an algebraic or actually a proof of the sandwich theorem, but we'll probably relegate that to the appendix. So there's the claim. Of course, we want to illustrate that. Yeah, some comments. Let's see. Once we have the formal definition of limit, we're good to go to prove the sandwich theorem. Yeah, let's bury that in the appendix. It's not that complicated, but a little heavy for Calculus 1. Let's illustrate the sandwich theorem. Sometimes it's called a squeeze theorem. I think that's kind of a term from yesteryear, a little more. Sandwich theorem is the common term because f is sandwiched between g and h. It's squeezed between g and h as well. And you might see the term squeeze theorem from some older calculus books. Okay, so let's keep that in the background and go through and do a few more examples. Oops. All right. So use the sandwich theorem to show the following. The limit as theta approaches 0 of sine theta equals 0, and the limit as theta approaches 0 of cosine theta equals 1. By the way, the sine of 0 is 0, and the cosine of 0 is 1. So it looks like there's some sort of substitution thing they're making an argument for here. All right, this is straightforward with the sandwich theorem if you believe the following. So we've got some inequalities that have been established previously. It's in the preliminary material. In section 1.3, we'll take this as given. It's shown that the sine of theta is sandwiched between negative absolute value of theta and absolute value of theta, and that 1 minus cosine theta is sandwiched between 0 and the absolute value of theta. Here's the pictures. So here's a graph of a sine function, and absolute value of theta. Okay, absolute values are these usual V symbols here. Y equals X style. Line with slope 1 over here, line with slope -1 over here. Take the negative of that, that just flips it about the horizontal axis. So here in yellow is the graph of y equals negative absolute value of theta. And the sine function is sandwiched between those two. So we'll take that as given, as we'll often do with these sandwich theorem applications to trig functions. And for the cosine function, let's see, we got 1 minus cosine, so not just a regular cosine function. We've flipped it over with this negative sign and then translated it up by an amount 1. Trust me, that's the graph of 1 minus cosine theta. It's bounded above by the absolute value as well, and it's certainly bounded below. I think I see a hint of yellow down below where they bounded it by 0, y equals 0. Bounded it below by 0, the horizontal line, the theta axis in this picture. And certainly 1 minus cosine theta is bounded below by 0. The cosine gets as large as 1 at 0, in fact, and again at 2 pi. So there is equality, but anyhow, the blue function is sandwiched between the yellow one, if you can see it along the theta axis, and the red one above. All right, so we have those sandwichings, which were given, say. Let's use the sandwich theorem to establish these. So we need to see what happens as theta approaches 0 for this function and this function. And what happens for theta approaches 0 for this function, the 0 function, I know what it does, and the theta function. And you can see from the pictures, you know what's going to happen. Okay. So we'll take first g of theta, in this one, part A, take g of theta to be the negative absolute value of theta, f of theta to be the sine theta that's sandwiched between g and h, and we'll take h of theta to be the absolute value of theta. So we've got g, f, and h. We know g of theta is less than or equal to f of theta is less than or equal to h of theta on some interval. about 0, c equals 0, except possibly c equals 0 itself. And by the way, it holds there as well, but it doesn't matter. Nobody cares. It's a limit question. Nobody cares what happens at 0. But the three functions are equal at 0, but not relevant to a limit question. That happens on some open interval. Yeah, how about this open interval? It happens on the whole real line. That's always true. You can see from the picture if you like. Yeah, except possibly it's C itself. That's for legal reasons, I guess I threw that in. Doesn't matter what happens, it's C equals 0. So we need to evaluate the limit as theta approaches 0 of g of theta, that is negative theta. Okay, maybe Dr. Bob's anthropomorphic definition of limit, it tries to pass through the origin, the point 0, 0. In fact, it does. The absolute value function tries to pass through the origin, so that limit L is 0. So it was a negative absolute value. I should have pointed at the yellow one. The red one does the same thing. The negative absolute value tries to pass through the origin. In fact, it does. The absolute value tries to pass through the origin. In fact, it does. So both of those limits are 0. So here's what we've got. We've got f sandwiched between g and h. The limit as theta approaches 0 of g equals 0. The limit as theta approaches 0 of h equals 0. Then we can conclude, since f is sandwiched between those two, that the limit as theta approaches 0 of f is also 0. And that's what we were trying to show. So we've shown the limit as theta approaches 0 of sine theta equals 0. You might argue, quite rightly, well, look at the graph of sine. It tries to pass through 0, 0 as well. Yeah, guilty as charged. I'm trying to illustrate the sandwich theorem here, though. Okay, so part B will do the same type of thing. We'll have G, F, and H and make similar arguments. For part B, take G of theta to be 0. So we'd have a horizontal line lying along the theta axis. F of theta, yeah, to be the blue function. H of theta to be the absolute value function. This occurs everywhere. In particular, say this interval, except possibly at 0. Yeah, it occurs at 0 as well, but nobody cares because it's a limit question. By Dr. Bob's anthropomorphic definition of limit, again, the g of theta function, right, it tries to pass through the origin, and it does, by the way. So the limit is 0. The h of theta function, the absolute value function, it's got a limit of 0. Again, tries to pass through the origin, close enough, then the limit is 0. And the blue function sandwiched in between. So the blue function has a limit of 0 as well. One little thing, we weren't asked to show the limit as theta approaches 0 of 1 minus cosine theta equals 0. We were asked about the limit as theta approaches 0, the cosine function. So we ain't done. Well, here you've got a limit of a difference. The limit of the difference is the difference of the limit. So we can rewrite the limit of that difference as the limit of the first, which is a constant function, gives us 1. Limit of the second, it's that thing we're looking for. So we get 1 minus the limit as theta approaches 0, cosine theta equals 0. All we did was modify this. We already had the limit equal to 0. This 0 is here. Rearrange it. Maybe bring this to the other side, and we get 1 equals the limit as theta approaches 0 of cosine theta, and that's what we were trying to show. So that establishes some limits for sine and cosine functions. We didn't touch these until now because we needed the sandwich theorem to deal with these, unless I go all anthropomorphic on you. And remember, none of that stuff's in the book. That's some things I made up. Still legitimate. These functions try to pass through the corresponding points. Okay, here's one that's a little more subtle, but it's the same idea. Suppose this inequality holds. 1/2 minus x squared over 24 is less than 1 minus cosine x, all divided by x squared, is less than 1/2. Suppose this holds for values of x close to 0, the book's wording. Let's elaborate on that. That is, this holds on some open interval containing 0 except at 0 itself. Come back and see me in section 10. That's probably the tail end of calculus 2, where that's actually established. We'll take it as given. So we're on our way for a sandwich theorem type hypotheses. We got this function less than this function less than this function. So this one's sandwiched between those two. It doesn't say less than or equal to, but if it's strictly less than, and it's definitely less than or equal to, it's the less than part. So they want us to explore the limit as x approaches 0 of 1 minus cosine x divided by x squared, the middle function. By the way, can you plug x equals 0 in this time? No, you get division by 0. Also, hey, that ain't a rational function. It's got a trig function in it. We know a tiny bit about trig functions, though. But you're doomed. Also, you can't factor cancel substitute. Can you factor an x squared out of a cosine function? Yeah, not yet. The tail end of calculus 2, you can. So maybe somewhere in chapter 10. But you got no way of factoring because of the trig function at this stage. Okay, well then let's define g to be the lower function, f to be the middle function, and h to be the larger function. We're looking at c equals 0 because we're taking a limit as x approaches 0. Well, we've got the inequalities. We've got g of x less than or equal to f of x less than or equal to h of x on some open interval containing c equals 0, except possibly at c itself. So we're good. Again, we've got strict inequality. So if you've got less than, then you do have less than or equal to. You've got the less than part. So looks like good hypotheses for the sandwich theorem. But wait, we've got f sandwiched between g and h. We need to make sure g and h have a limit as x approaches 0 that's the same. The limit as x approaches 0 of the g function, oh, it's polynomial, I can just substitute in. Limit as x approaches 0 of the h function, well, that's just a constant. So the limit is a half for that one. So limit as x approaches 0 of g of x, that is the 1/2 minus x squared over 24 stuff. You can plug in the 0. Why is that? Because it's a polynomial. Theorem 2.2 justifies that. And the limit as x approaches 0 of a constant function is the constant. It's note 2.2.a in the notes. So we've got 1/2 out of both of these. F is sandwiched between g and h. G has a limit of a half. H has a limit of a half as x approaches 0 in both cases. That is, limit as x approaches 0 of g of x, limit as x approaches 0 of h of x, those both equal a half. We've got the sandwiching thing going on. So the sandwich theorem says, well, then the limit of the f of x function, the one sandwiched between the other two as x approaches 0, must also be a half. So that limit's a half by the sandwich theorem. That's what this information tells you, and that's how they worded the question. At this stage, without the sandwich theorem, you couldn't have done this one. So this one is necessarily the sandwich theorem. I don't think any of you can get a very good graph of 1 minus cosine x over x squared. The place that cause you a problem is at 0. I don't know, with this information, maybe you can. This really can be done with factor cancel substitute as well, it turns out. It's a long story, a story that involves taking this cosine function and writing it in a different way, writing it as a power series, it's called. That's probably the content of section 10.9. But for us, we got to do it with the sandwich theorem. They gave us a question that was totally designed to be addressed with the sandwich theorem. Okay, another limit, a little oddball question here. It says if the limit as x approaches 4, f of x minus 5 divided by x minus 2 equals 1, then find the limit as x approaches 4 of f of x. Okay, we'll justify our answers with all the little rules we have. We're taking a limit of a quotient. Well, the limit of a quotient is a quotient of the limits, if we don't get 0 in the denominator. This involves a limit of a difference up here, so we can write that as the difference of the limits. We could do a similar thing in the denominator if you like. I didn't. We've got a polynomial in the denominator. You got a polynomial in the numerator? I don't know. I don't know anything about the f function. It may not be a polynomial. You know, it could be a logarithm or a exponential or not a polynomial, a square root, I don't know. So we can write the limit of the difference is the difference of the limits. We can substitute the 4 in this x minus 2. What kind of function is x minus 2? It's a polynomial. Theorem 2.2 says you can evaluate limits of polynomials by substitution. Oh, and we don't get 0 in the denominator, relieving any concerns you might have from using the quotient rule up here. So 4 minus 2, that'll give us a 1/2. Let's bring that out front. We'll have 1/2 times this limit that we're looking for, minus 1/2 of 5. Let's write that as negative 5/2. So we've got the limit we were given equals this quantity here. You were told that limit's 1, so I know this quantity here is 1. Remember, we're looking for these symbols here. The limit as x approaches 4 of f of x. Okay, we were given the limit of the given function was 1. We just showed the limit can be rewritten in these terms, so this equals 1. So here's a little equation. We'll solve for the unknown. The unknown's involved. It's the limit as x approaches 4 of f of x. Let's multiply both sides of the equation by 2. Gets rid of the denominators, introduces a 2 on the right-hand side. We're looking for this, gets this thing isolated. Let's add 5 to both sides. That'll leave you with the limit equals 7. So it's practice in using the limit laws, the limit rules, the Theorem 2.1 stuff, and then a little arithmetic. So it became just arithmetic once we got the equation set up here. And excellent, that completes section 2.2. Okay, excellent. I will see you soon in section 2.3. 2.3 is pretty intense. We're going to take these informal ideas of trying to pass through points and things like that. We're going to make it mathematically rigorous. We've gone through these intuitive things to soften the blow of dealing with the rigorous math. We got to do it. It's the foundations of all of calculus. But in the next section, we'll go through a rigorous definition of limit. We'll establish some stuff and spend most of our time in the next section trying to dissect what that rigorous definition of limit really means. You'll come to appreciate the idea of a graph tries to pass through a point once we get through all this rigorous stuff. You'll do fine. I'll see you in section 2.3 in just a little while. Have a nice day.